Okay, here we go. Our first actual example of computing a line integral. And so I'm going to actually probably start calling these scalar integrals at some point to distinguish them from vector integrals. Right now, the function that we are integrating, our integrand right here, that's a scalar valued function. It's a number. It has one coordinate, right? But we're going to be looking at integrating vector fields, in which case the thing that goes in here is going to look like a vector field. So I might refer to scalar or vector integrals. But anyway, so gotta walk before you can run. So first let's do some line integral examples. So we're going to be integrating 2 plus x squared y with respect to arc length over this curve right here, this upper semicircle. And so the first step is going to be to choose a parameterization. And so we'll just use the standard thing, cosine t sine t, to get us around the semicircle. And then we also have to write down our parameter domain. So we've got t going from 0 to pi. So that'll take us around the semicircle here in a counterclockwise direction, the standard positive orientation. Okay, so now the thing to note about this, and this is the important thing to keep in mind that makes everything run for this section, is that this parameterization means that x, which we're now thinking of as x of t, is cosine t, and y, which we're thinking of also as a function of t, is sine t. So this is going to determine how we substitute into into the integral. Okay, so then we take that integral, integral c2 plus x squared y, and here, let me just label this actually. So this is going to be the substitution referred to into at the end of that last line there. So we're going to substitute our parameterization in here. So we're going to switch now to the parameter domain, and we've already written down the data to put in there. So that's for the bounds of integration. So we're going to go from 0 to pi, because this is going to be a dt integral. And then we've got 2 plus, and then we look to our x. Here's our x. And then we look to our y. Here's our y. So this is our new and improved version of x squared y. And then this is going to be with respect to arc length. So let's see. So this whole thing now is going to be multiplied by, and ds is going to be right here, c prime t dt. So let's see. Now we need to put in c prime of t, which is the speed. Now, for this particular path, I can take a cheater shortcut, because this is going around a circle of radius 1 in pi seconds. That's how much time it takes. Think of t as time, right? And that's exactly the length of this curve. It's pi. So if we go a distance of pi and a time of pi, then that means our speed is 1. So we're going at unit speed. It would take us 2 pi seconds to get the full distance around the circle, right? Okay, so I know that the answer here is actually going to be 1. Now, that was a sneaky shortcut. Let me show you how you would do it in general. What you would do is you'd say, okay, well, we figured out what our c of t is. That's the thing that we need to take the derivative and magnitude of. So down here, I'm going to write the derivative, if I can get the right pen selected. So this is minus sine t comma cosine t, just by differentiating each coordinate. And then the magnitude of this guy is minus sine squared t, Oh, I put the square in a bad place. There we go. And then from this, so this is the expression that you would substitute in at this point right here. And for us, as we saw, this thing just evaluates by Pythagoras' theorem to 1. So we're good to go. Okay, so now we've got this integral, and you can just go ahead and integrate it. It's cosine and sine. So what do we get? So we get something like 2t minus cosine cubed t over 3. And so that's just doing a u substitution. I mean, you can work this one out on your own, and I doubt it'll take you much time. But if you put cosine t, then your du is minus sine t dt, and then you've got a u squared right here for doing your u substitution. So, and okay, so that's going to be from 0 to pi, and then when we evaluate that, we get 2 pi plus 2/3. Okay, there you go. That is our first line integral. So not much to it. You just got to remember this idea that first you set up your parameterization, and then you use that as your rule for this is my x and this is my y. All right, so while we're on this example, I want to show you something else, a feature about this which is going to actually turn out to be important later. So suppose we close up the semicircle. So we just did over the top. What if we now go across the bottom? So we're going to go from -1 to 1, and we're going to do the same integral. All right, so let's see. So the first step, I would need to figure out a parameterization. So let's see. So the standard way to get, so the path from A to B, this straight line path, I guess I should say. So this is one you should definitely have memorized, is that, let's see, so we start at A, and then we go T in the direction from A to B, right? And so that's A plus T times, and the direction from A to B is B minus A. And so then that means we've got 1 minus TA plus TB. So it's kind of like we're splitting up a fraction, right? Like if T was 1/2, we'd have 1/2 here and we'd have 1/2 here. So you'd have the midpoint formula. If T was 1/3, then you'd be, you'd have 1/3 of B and 2/3 of A. So let me just draw a little picture. Here's A, here's B. And so C of 1/2 is going to be the midpoint. If we had C of 1/3, then we'd have 2/3 of A and 1/3 of B. So we'd be there. If C is 2/3, then we'd have 2/3 of B and 1/3 of A. So we'd be over here. So this is the kind of path that you get. And in particular, check out like what happens at C of 0. Well, when T is equal to 0, this part's just gone, and this part's just A, so you're at A. And what about C of 1? When T is equal to 1, this part is 0, and this is just B, so you're at B. Okay, so the straight line path from one point to the other here is C of T is going to be, let's see, so we're going to start from -1, 0, and then we're going to, I should have left space, 1 minus T that part, and we're going to T times the part that's where we end. And so that'll get us there as T goes from 0 to 1. And so then I can just do the arithmetic to put this together. So I have T minus 1, 0, plus T0 or 2t minus 1, 0. Now, that's not the only way to parameterize this path. You could have done something else. Like probably some people were looking at this and go, oh, well, duh, I just need to move the x coordinate. So I could just kind of write this down as, let's see, we're going to start at -1, so I'm going to have like -1 plus t, my y coordinate is never going to change, and we're just going to do that, let's see, so we start when t is equal to 0, and we're going to have to go all the way up until t is equal to 1 to get our x coordinate up to 1. Sorry, we're going to have to let t go all the way to 2 to let our x coordinate go, get all the way up to 1, right? That's perfectly fine. That would probably be the simple way, actually, to do this one. Now, what you see is that this one moves at speed 2. See the derivative right there? The derivative of this is giving you the speed. Moves at speed 2 for 1 minute. This one moves at speed 1, the coefficient of t is 1, for 2 minutes. So it just goes slower. That's fine. It doesn't matter. The speed that you go at, it should not matter. It will be, the ds will compensate and make up for the fact that you've chosen one path or another. So you'll always get the same answer. So do whichever one seems nice for you. Okay, I guess for whatever reason, I'm going to go with this one here. Let's go ahead and do that. So now I go back to the integral. So this is 2 plus x squared y ds. So now I make use of that substitution. Here we've got x, and here we've got y. And so this is going to give me, let's see, so I'm going to go, and I'm also, since I'm using this parameterization, I'm going 0 to 1. If I were to use the other parameterization, I'd go 0 to 2. Okay, and so then we've got 2 plus, and I've got 2t minus 1 times 0. And then I'm going to need my speed for the ds. So I can see it by staring, but I'll just write it out. So when I differentiate the first component, I get 2, and the second component, I get 0. So my speed there is 2. And so this is 4 times the integral, which gives me 4. Okay, a couple of things to notice, and maybe this does not seem significant at all at this point, but I want to point out just how important it is that, in fact, 4 here is not equal to 2 pi plus 2/3, which is what we got by going over the top of this curve. So path matters, at least for this integrand. Later on, in the next section, I think, or maybe the one after, we're going to see that there's some special integrands for which the path does not matter at all. And in such cases, if you were to go in a complete loop, closed loop like this, the integral would vanish. And so that's a very special thing. But this is just an example so that when you see that later, you'll realize, oh my God, that's so special. I remember back when we were doing 16.2 that like we did path integrals and we got different answers by going different paths. So just file that away for like how cool that is. It doesn't seem cool now. Later it'll seem cool. And then the other thing that I wanted to point out is that it doesn't matter which way we went along the bottom path. So in other words, once we've chosen, or once it's determined that we're going to be following this bottom part right here, the fact that we went from left to right is immaterial. If we'd parameterized it to go from right to left, we would have had the same answer. And that's a little counterintuitive because you're used to looking at integrals with respect to x. And in that case, if you go from right to left, there's a sign change, but that's because this guy sees the direction that you're going in as left or right. When you look at this guy, hey look, there's an absolute value sign. It's not going to notice which direction you're going. And that is going to be something also that is different from when we do vector integrals. For vector integrals, we're not going to be using ds. We're instead going to be using dc, which is just c prime of t dt with no absolute values. That one will see the direction that you're going in and whether or not you're moving into a force field or away from a force field. Sorry, I shouldn't call it a force field. Into a vector field or with a vector field.